Let's take a look at reactions of acid halides. Because acid chlorides are so reactive due to the stability of the chloride, and hence the chloride being a good leaving group, we can displace the chloride with lots of different things. For example, if I take a chloride or an acid chloride and I react it with an acetate, I can replace this chloride with my oxygen, giving me an acid anhydride. Similarly, I can replace the chloride with an OCH3 to form an ester under neutral conditions. Now you'll remember the previous slide I had a methoxide where there was a solid minus charge on this oxygen, but I can also do that under neutral conditions. What are the mechanisms of these reactions? Let's look at the first one. I have my acid chloride. My acetate anion comes into that carbonyl carbon, pushes the electrons up onto that oxygen, giving me this tetrahedral intermediate. The negative charge then comes down, closes like a door to form a double bond, and kicks off the chloride leaving group. This gives me my final product, which is an acid anhydride, and my chloride leaving group as a byproduct. What is the mechanism of displacing the chloride with an alcoholic group? Well, here's what I do. I have my alcohol, in this case methanol, reacting with my acid chloride. The electrons come in, they hit that carbonyl carbon, thrusting the electrons onto that oxygen and giving me a tetrahedral intermediate. I hope you're noticing how repetitive these mechanisms really are. Once I get to that tetrahedral intermediate, the electrons on the oxygen come down and kick off my chloride leaving group, giving me this temporary intermediate. To neutralize this oxygen, the chloride then comes, grabs that proton, and pushes these electrons into the oxygen. That gives me my final product, which is an ester, and hydrochloric acid as a byproduct. Hence, we can see that we can also form an ester from an acid chloride using a neutral alcohol rather than a methoxide or an alkoxide anion. Another reaction that we can do and can imagine is displacing this chloride with an OH. That can be done under neutral conditions by treating the acid chloride with water. Acid chloride, or the electrons on the water come in, electrons go up, then the electrons come down and kick off the chloride, giving me this intermediate, and then a base, which could be the chloride or it could be solvent, comes and deprotonates this to give me my carboxylic acid product. We can also convert acid chlorides into amides, that is, replacing the Cl with an NH2 using ammonia. What is the mechanism of that? Well, you'll probably see a lot of repetition here. I have my acid chloride sitting there, and my ammonia, that is the lone pairs on the nitrogen in ammonia, come into this carbonyl carbon, thrusting the electrons up onto the oxygen. This negatively charged tetrahedral intermediate sits there momentarily, and then the electrons come down and kick off my chloride leaving group. That gives me this intermediate. The chloride can then come around, deprotonate that compound, neutralizing the nitrogen's positive charge and giving me my amide, along with HCl as a byproduct. There are reactions I can do to either form or convert acid anhydrides to other products. In this example, I have sodium formate being reacted with an acid chloride to form an acid anhydride. We talked about that earlier and showed the mechanism, but I'll probably show it again. I can also convert acid anhydrides to esters by reacting them with alcohols. What are the mechanisms for these reactions? Well, naturally, I'm going to show you. In the first reaction, I've got this formate interacting with an acid chloride. Electrons on this oxygen that has a negative charge come in, thrust up onto this oxygen, giving a minus charge. This is my tetrahedral intermediate. And then those come back down and kick off my chloride leaving group. This forms a double bond and gives me my acid anhydride product and my chloride byproduct. The mechanism of the second reaction is also similar. I have an alcohol that comes in to one of these carbonyls. It doesn't matter which one because this acid anhydride is completely symmetrical. Those electrons then get thrust up onto the oxygen, giving me this tetrahedral intermediate. This O- comes back down, collapses to give a double bond, and kicks off this as my leaving group. This gives me this intermediate. Of course, I have this protonated oxygen that's positively charged and not happy. So this acetate that was my leaving group from this step deprotonates, thrusts the electrons into that oxygen to neutralize the charge, and gives me my ester product. And you'll notice that when this O- steals that proton, it also forms this carboxylic acid byproduct. This kind of reaction can be applied to acid anhydrides in numbers of different ways. If I take hydroxide, for example, and I deprotonate this phenol, the O- can come in here, electrons go up, electrons go down, and kick off my acetate leaving group. This forms this kind of product, which is an ester from salicylic acid. This should look familiar to those of you who have taken my lab class last semester, because we ran this reaction in the lab. We took salicylic acid and treated it with acetic anhydride to make aspirin. Another reaction that we can do is treating an acid anhydride with water to form carboxylic acid. I'm going to show the mechanism of this on the next slide. Here's my acid anhydride. I have water. The lone pairs on the oxygen come in. Once again, electrons go up, giving me this tetrahedral intermediate. Now this O- electrons are going to come back down and kick off this acetate leaving group. That gives me this intermediate. Now you'll notice that this oxygen is positively charged and wants to be neutralized. We can have that occur by having this acetate, which is the leaving group from the previous step, come and deprotonate, thrusting these electrons into that oxygen to neutralize it. You'll notice that we make our carboxylic acid product, and when this O- steals this proton, it also makes the exact same product again. So when we take an acid anhydride that's symmetrical at least, and hydrolyze it with water, we in reality get 2 moles, or 2 equivalents, of carboxylic acid out the other end. The remaining reactions I will not be showing mechanisms for, but they follow the exact same pattern as the mechanisms that we've shown thus far. Consequently, I can treat an acid anhydride with an amine. It can be an amine that has an alkyl group on it or not. And the electrons on the nitrogen will come into this carbon. Electrons go up, electrons go down, kick off this yellow highlighted leaving group to form an amide. Here's a neat example of that. If I take this compound, p-hydroxyaniline, the nitrogen electrons can come in and attack acetic anhydride here. Electrons go up, electrons go down, kick off this green group, and I form this compound, acetaminophen, which you guys will probably be very familiar with and have very likely taken to treat your headaches.